Thank you. Thank you so much. Thank you to the organizers for inviting me. Really enjoyed myself at this conference. A very nice place, a nice meeting. So thank you very much. I'll tell you about some recent work that's done with my postdoc, Bimla, and with a summer student from not very far from here, from IISc Bangalore, who did some very nice work. Pointer allowing, we will go to the next slide. It's working now. Okay, so the first introductory slide, which most of you have probably seen. So let me consider a square with two kinds of interactions, with spins on a square. Suppose I have a J1 interaction on nearest neighbor bonds and a J2 interaction on next nearest neighbor bonds. Both of them are antiferromagnetic. They both want the spins to be anti-aligned. Now this is a classic case of frustration. So if I wanted to make the J1 bond happy, I could put the two spins anti-parallelly along a side of the square, but then you wouldn't know how to put the third spin. If you put it up, this bond is happy, but this bond is unhappy. So you cannot maximally satisfy all the bonds in this configuration. That's why we call this a frustrated system. We have these competing interactions, J1 and J2, that compete against one another. So we can think of this problem on a full square lattice with J2 over J1 as a tuning parameter. So I'll be talking about this model initially. This is a very well-known problem. This is perhaps the archetypal problem of frustrated magnetism. So I have a square lattice with J2 over J1 tuned. In the classical limit, that is, if I take my spins to be just vectors, three-dimensional vectors, with all components commuting, then the phase diagram is well known. You have a nail state, which is just an antiferromagnet, and a stripe state. And there's a phase transition at J2 is J1 over 2. This is a special point. We will see more about this point in just a bit. But suppose I think of quantum spins. I think of spin half spins that have the spin commutation relations. Immediately, all hell breaks loose. There is still a nail state and a stripe state. In the middle, there is a domain in which there is no magnetic order. So there is neither an antiferromagnet, nor a stripe, nor a spiral, no magnetic order. So this is mother of all frustrated magnetism problems. So every method that can be conceived of has been used to describe this problem. That itself is okay. It's just that every conceivable answer has also been found. So everybody claims a different answer for what's happening in the middle. So clearly something is wrong. Right? So this is not even an exhaustive list in the paper we were given. There's still half a dozen more that wouldn't fit in this slide. So I didn't put that many. So you can see there are very different methods. They've all used different, they all have their own limitations. And there is no exact method. It is a frustrated problem. And depending on which method you use, you get a different answer. And even the boundaries of this phase, they depend on which method you use. So clearly something is up, and we need some new physics ideas to make progress. If you have to understand this problem, you have to think of why you get so many answers, how you can fix this. So that's what I'll try to do. I will not solve the problem, but at least there'll be some hints as to why you see this, why you can pick the answer you like. All right. So let's first think of this special point. This J2 is half of J1. This J2 is half of J1. In this case, the classical problem has a very special form. So you can write it as a sum over squares. You can write it as J1 plus S1 plus S2 plus S3 plus S4 whole square. And you can see this is true fairly easily. So the J1 bond is shared by two squares. But the J2 bond only occurs in one square. When you expand this sum, you get terms like S1 dot S2, but that will occur two times in two squares. But this bond will only occur once. And therefore, this is an accurate representation of the parameter. So immediately you see that I pressed the wrong button. You immediately see that the energy is a sum of positive terms. So the ground state, to choose the ground state, all you have to do is you have to find a way to make S1 plus S2 plus S3 plus S4 0 on every square. So if I'm able to assign S1 plus S2 plus S3, S1, S2, S3 on the square lattice such that the sum is 0 on every square, then that's guaranteed to be a ground state. Now you can easily convince yourself that this has infinite degeneracy. There are many infinite number of ways of doing this. This is a little like the spin ice problem. You can easily convince yourself, a sheet of paper, that this is true. So I have a low, it's more than linear in the system size. So suppose I have an L by L lattice, it's at least, there's a lower bound is at least L. This I can show easily. But the exact bound I don't know. Classical. Right, so there are at least, right, correct. So, suppose I have L by L lattice, I have at least L continuous parameters that are free. Continuous parameters that are free. Right. And there are more, there are actually more, but I don't know the exact one. So it is this high frustration that allows for several competing phases. So you actually have many, many possible ground states. They're all very close by in energy. Now when you put quantum fluctuations, they pick different states. Now, depending on which method you use, you pick one state. The energy difference is so small, it's very hard to pick the correct state. That's why we get so many different answers. So we'll try to resolve this a little bit, and we'll try to do this by using a tuning knob. So we will introduce another interaction, which is a ferromagnetic J3 coupling that lifts this degeneracy in a suitable way, in an elegant way. So let's see how the J3 acts. J3 is this bond. So it's ferromagnetic here. This is the interaction we're putting in. And it wants this spin to be the same as this spin. Similarly, this spin to be the same as this spin, so on. So you can see that whatever configuration I have on this square, it wants to repeat the same configuration on this square. And so you get all the shaded squares are actually the same configuration. That's how you minimize the J3 term energy. And so what you have to do is you have to simply fix a 4-site magnetic unit cell. I have to fix S1, S2, S3, S4 on one shaded square. And then the shaded square itself should satisfy the zero-sum condition. S1 plus S2 plus S3 plus S4 is 0. And automatically you can see that the unshaded squares also satisfy this condition. So if I put S1, S2, S3, S4 and I repeat this, you see the unshaded square is also S1, S2, S3, S4. The sum is automatically 0. So as long as the sum is 0, the J1-J2 part is minimized. And if this configuration repeats here, the J3 part is also minimized. So any configuration that satisfies this is a ground state of this problem with the J3 model. So now I will show you now that this corresponds to just 2 independent parameters, theta and phi. That's all you have left to fix the ground state now with the J3 term. Okay, so now I have to fix 4 spins, S1, S2, S3, S4, such that the sum is 0. These are the 4 spins on one square. And now I can do this with 2 parameters. So here's a picture that explains this. Let me first pick all the 4 spins to be on one plane. So this great circle. And let's say S1 and S4 are opposite, S2 and S3 are opposite, and the angle between them is 2 theta. So I fix that as one parameter. I still have one more parameter left, which is to rotate the 2 spins in the bottom by an angle phi. So you can convince yourself that up to a global rotation, this fixes all possible configurations that satisfy this condition. So now, all I'm left with are 2 parameters, theta and phi. Once I fix them, I fix the ground state of the problem. So now this, we've gone from infinite degeneracy to just 2 continuous parameters, so it's much, much smaller. And there's a more elegant way of looking at this, which perhaps we'll look at now. So let's go back to the J1-J2 problem, and let's look at how to quantify the number of ground states. Not precisely quantify, but. So let's propose a spiral ansatz. Let's say the spin configuration is given by something like this. So I choose the XY plane, and I decide that the spin ground state should be a spiral with a pitch vector Q, and let me try to optimize over Q. If I do this, you find that in this region where J2 is small, you find that there's only one Q that satisfies this, and this is pi pi. This is why you get a Nail order in this region. And when J2 is greater than J1 over 2 in this region, you find these 4 points. Actually, there are only 2 distinct points. They correspond to 2 stripes. You have stripes either running horizontally or vertically. So the 2 cases. But exactly at the point in the middle, this J2 is J1 over 2, you get a whole, you get an infinite number of Q points. Any Q that's on the Brillouin zone boundary is a minimum of the energy. So this characterizes the infinite degeneracy that we have in a different way, in momentum space. So now what we've done by introducing the J3, the ferromagnetic J3 coupling, is to cut this down. So with a ferromagnetic J3, you only pick, you pick a combination of these and these. So you get there are actually 3 distinct wave vectors, one here, one there, one there. That's the ground state manifold. So I can form spirals with Q1, Q2, or Q3, and only those 3 are a minimum of the ground state with this ansatz. But we'll clearly see there's actually much more than that. So let me go to the full phase diagram. So this is J2 and this is J3. This point is J2 and J3 both 0. And now I've used the spiral ansatz for the whole phase diagram, and I've tried to map out the phase diagram. So in this region, you get a nail state. There's just pi, only one minimum vector, only one minimum wave vector for the spiral. In this region, you have two minimum wave vectors, which is the striped wave vectors. And here you get some incommensurate wave vectors. But this line, the line of interest, is what we're looking at. So we've started from this J2 is half of J1, and we've put in a ferromagnetic J3. And you see that this is actually a phase boundary between the nail and the striped phases. That's why we get both the wave vectors. And now there's something special to these three wave vectors. So the three wave vectors were Q1, Q2, Q3, I said. The three of them satisfy this property that 2 times Q is a reciprocal lattice vector. 2 Q's equivalent to 0. Therefore, they have a special property that these three spirals can coexist. So let me show you how that happens now. So let me consider, so we've shown that there are 3 Q's. Earlier, we were only considering 1 Q at a time. So this is just as a single Q. Now let me write a coexisting spiral ansatz, which has all 3 Q's. I've omitted the sine Q dot R terms because sine Q dot R for these Q's is uniformly 0. Again, you can check. So I've introduced 3 vectors, U, V, W, arbitrary vectors, and this is a coexisting spiral ansatz. And now I can ask, is this a legitimate spin state? For this to be a legitimate spin state, the spin length should be uniform. Every side, the spin length should be S in some direction. Yes? Yes. I mean, Q and minus Q, that's all you can superpose. You can't even do Q1 and Q2. So now I impose this additional constraint that the spin length is uniform at every site. And in terms of these U, V, W vectors, that gives me 2 conditions. And this you can easily work out, this from the spin length. And as long as you satisfy this, this is a legitimate spin state. So when you look at this condition, this is actually equivalent to saying that there's a 4-site magnetic unit cell with total spin 0. So this picture is exactly equivalent to that shaded square picture that we were drawing a little while ago. There, you can actually see that exactly equal. So you get 2 free parameters there, theta and phi, we discussed. Here also, this amounts to 2 free parameters. If you actually work 2 free parameters and the global rotation. Okay, good. So now let's look at the degeneracy at this point. So this was the problem point, where we had many answers. So here, we saw that if you do the spiral ansatz, you get any Q on the Brillouin zone boundary is a ground state. But I can still ask, what is the ground state manifold? How many classical states are there that are ground states of this problem? And the ground state manifold actually falls into 2 sectors. In one sector, I have single spiral states. So I can choose any Q on the boundary, and I can make a state like this. That's one sector, and that's already an infinite number of states. And you have coexistent states. You have multiple Qs, 2 Qs or 3 Qs, that can be formed. But these can only be formed with Q1, Q2, Q3. You can only choose these. You cannot form coexistent states with some arbitrary Q somewhere there. This is, again, also you can show it fairly easily. So what we've done by introducing a ferromagnetic J3 is we've picked this sector only. So we've cut out this sector, and we're looking at this sector. Now, that, you can see, reduces this problem. It makes it more tractable. We've reduced the classical degeneracy there. We ask, can we find the ground state of this problem? And hopefully, it'll help us later on to decide what the ground state is there. Okay, so now let's look at this with the ferromagnetic J3. So now I have a J2, which is half of J1, and J3 is ferromagnetic. And the ground state is just these shaded squares. And there are two free parameters, theta and phi, that I need to fix the spins on one square, and then every other spin is fixed. Everything distributes. So there are, this is also an infinite set of ground states. Here are some example ground states. For instance, you can choose a nail state, this up, down, up, down, up, down, up, down. Or you can choose a stripe state, up, up, down, down. You can choose all the spins to be coplanar or tetrahedral. You just need them to satisfy this condition. Here are some candidate states. So we can look at this ground state manifold. We can look at each of these states. For instance, here are the 4 states, nail, stripe, coplanar, tetrahedral. And we can do a spin wave analysis for each of these states. And this is the spin wave spectra, so energy versus momentum. And we see that there are 2 kinds of Goldstone modes here. So we find 2 modes. One is, we find some modes are linear, and this is true for any state in that 2-parameter family. one kind of Goldstone mode is linear, one kind of Goldstone mode is quadratic. This is already very interesting. Usually we find linear modes in antiferromagnets, quadratic modes, ferromagnets. Here we find both of them coexisting. They both give the same spectrum. So yes, so equations of motion or Holstein-Fomalhaut. These are all still ground state manifold. They're all ground states still. So it's still. So in the quantum approach, I can do Holstein-Fomalhaut spin wave theory for spin S. And then you find that there's a classical energy and there's a quantum correction, this 1/S correction. So you can examine this quantum correction and see whether it breaks the degeneracy of the manifold. For instance, you see that here are the 4 candidate states we showed. There's Snell, strike, coplanar, tetrahedral. And this is J3, it's being cut off. J3 zeros here, J3 decreases here. This is the energy. You see that the Snell state is always has the lowest energy. I'm actually plotting the energy correction term. They all have the same classical energy, but the quantum correction is lowest for the Snell state. The Snell state wins. So there is some more, for those of you who might know spin wave theory, you can calculate the correction to the Snell moment, to the linear order correction in S. And you see that the correction becomes of order half when J3 is 0.1, minus 0.1. So what this is telling us is when J3 is very small, less than minus 0.01, then the Snell state is unstable. Our ansatz is not consistent. But let's not worry about that too much. So what we've done here is we've plotted this energy correction as a function of theta and phi. So theta, phi define a sphere. On the sphere, we can plot this energy. You see that the energy has a well-defined minimum at one point. And that one point corresponds to Snell order. So of all this, you had a 2-parameter continuous family of ground states. And when you calculate the quantum correction, it's the Snell state that has the lowest energy. Snell state wins. There is actually some very nice classical, let me skip that, thermal results also, but let me focus on the quantum case. So now, so we've shown that spin waves select Snell ground states. We already know that, so when we started from this this problem, here the ground states, we found many different ground states. Once we put in this extra J3 term here, you already see that the Snell state wins. There is a clear magnetic order. So the degeneracy has been reduced, and we can identify a ground state. So this was spin wave results. So let me show you results from exact diagonalization as well. So this is exact diagonalization using Lang's algorithms for 16, 20, 32, 36 size clusters. And what we plotted here is the Snell moment. So this is like, we take the ground state and we calculate the Snell moment. So perhaps it's better to see that. So this is, so let's say J3 over J1 is 0. And this is for different system sizes. We plot this Snell moment. And we see that it extrapolates to a negative number in the thermodynamic limit. So that indicates that Snell state is not consistent. This is not the valid Snell state. However, for J3 is less than minus 0.2, then you have a well-defined Snell state. So exact diagonalization is also consistent with these results. So when you put in a ferromagnetic J3, but you have to put in a sufficiently large ferromagnetic J3, greater than minus 0.2, it's minus because it's ferromagnetic, then you do get a Snell ground state. For smaller values of J3, you don't get a Snell state. You get some other state, okay, which we don't know. So now let's actually, so there's some more interesting physics here too. So this was the J2-J3 phase diagram. In the classical model, we had a Snell state and the stripe state, and there was one line here that was the phase boundary between the two. But along this line, we've already argued that quantum fluctuations select the Snell state. So clearly, although along this line is the phase boundary, the classical energy is the same for the Snell and stripe phases, but the quantum energy is lower for the Snell state. So the Snell state actually pushes into this classical stripe region. This is a phase diagram from exact diagonalization. You can work out the phase boundaries. So we see that the Snell state eats into the classical stripe region a little bit. But this is just an aside. Let's not worry. So in the red region, neither nail order nor stripe order is consistent with ED data. In the blue region, it's hard to tell. So we cannot, with finite size data, we cannot decide what the nature of the state is. Yes, it's stripe here and it's nail there, classically. So classically, this to the left of this line is always nail. To the right of this line is always stripe. Right, so that is, I'm only looking at ferromagnetic J3. So to see that, you have to go antiferromagnetic. And there, this breaks down. So in the classical ground state, you are allowed to get coexisting spirals. Right. Yes, that's exactly at that line and with the negative J3, so along this line. But that's in the classical model. The quantum model, we see nail state. So now I've argued that if I have the J1-J2 model with J2 is half of J1 and with the ferromagnetic J3, the classical ground state corresponds to a magnetic unit cell with 4 sites. So I have to fix spins on one shaded square and then that remains. So this indicates that even in the quantum case, I could have a 4-site wave function. I could have a wave function that's factorizable over plaquettes. I need to define a wave function for this square, then there's the same wave function for this, but these two are not entangled, so I can just write it as a direct product of plaquettes. That is suggested by suppose I take that as an ansatz, and then I try to find this Plaquette wave function variationally. What we find is that so this is J3 axis, I'll tell you what this is. So here is J3, we're tuning J3 here. So for small J3, we find that the Plaquette wave function that minimizes the energy is actually a Plaquette RVB state. It's an S-wave RVB state. It's a linear combination of 2 dimers. So on the shaded squares, we have up, up, plus down, up, down, horizontal plus vertical. And then this wave function just repeats. So this is what we get from this variational ansatz. But as you increase J3, you make it more and more negative, more and more ferromagnetic. You see that we actually get a nail ground state. So there is a triple-on condensation transition. You actually see that the spin gap reduces, goes to 0, and then a nail moment builds up here. So this is the nail moment here. It increases here, so clearly there is some transition here. So this again is consistent with the fact that at small J3, you have a disordered phase. At large J3, you get an antiferromagnetic phase. So that actually brings me to the summary, but if there's time, I could show you some more results. But let me summarize what I have now. So we discussed this quantum disordered phase in the square J1-J2 antiferromagnet. And we discussed that the root of this disordered phase is an infinite degeneracy in the classical model, many, many ground states. And to make headway with this, we introduced a ferromagnetic J3 that partially lifts the degeneracy. And the remaining degeneracy can be thought of in 2 ways. It can be thought of as a 4-site magnetic unit cell or as coexisting spirals, momentum space or real space. And with this J3 coupling, this quantum disordered phase gives rise to nail order. It just becomes an antiferromagnet. So with the reduced degeneracy, you get an antiferromagnet. The ground state is not ambiguous anymore. This picture is consistent from spin wave theory, from exact diagonalization, and from a Plaquette factorized variation approach. So what this tells us about the original J1-J2 problem is that the quantum disordered phase that we see there is still arises because of some classical degeneracy. But it's actually the other sector. It's driven by the classical degeneracy of single spiral states, not by the classical degeneracy of coexisting spirals. Even with the J3, we do have these coexisting spirals, but we still get nail order. So this suggests that suppose we took the J1-J2 XY model. XY model cannot have coexisting states simply because spins are constrained, or can have very limited coexisting states. And this should have the same ground state as the J1-J2 Heisenberg model. So we should be able to adiabatically tune from the J1-J2 XY model to the J1-J2 Heisenberg model, get the same quantum disordered phase. Okay, so I still have 4 more minutes. So since I have 5 minutes, let me show you some more results. So earlier on, I showed you, okay, so now I've discussed the quantum problem. So let me step back and let me look at this purely as a classical problem. So I have the J1-J2 model with the ferromagnetic J3. So this is a classical spin model. And I already showed you the spin wave dispersions in some selected cases. We also discussed that the ground state has two free parameters, theta and phi. So we can think of this as a classical problem with spin wave excitations. And in the limit of low temperatures, you can find the free energy that comes about due to spin wave excitations. So this is the expression for the free energy, which can be worked out. And here we are plotting the free energy versus theta and phi. These are the two parameters that characterize the ground state manifold. And now you see that there are actually three distinct minima. So when I plotted the quantum ground state correction, there was only one minimum, but now there are three minima. This tells us, and the three minima correspond to Néel order, horizontal stripe order, and vertical stripe order. So there are three distinct ground states. They all have the same free energy. From our two-parameter continuous family, we've reduced it to three discrete states, just three possibilities. So this tells us that at very low temperature, this is after all like the low temperature expansion, there are three equivalent states. The system won't know which one to pick. And it will pick one of them at random. That corresponds to Z3 symmetry breaking. So this is like a Potts model symmetry breaking. And sure enough, when we do classical Monte Carlo simulations, and we are looking at the spins and we're looking at their behavior at finite temperatures, we see a phase transition. So let me remark that at any non-zero temperature, you'll immediately lose spin rotational symmetry. So you cannot have an antiferromagnet at finite temperature 2D. This Mermin-Watling theorem prohibits that. Nevertheless, if the ground state breaks a discrete symmetry, which is Z3 symmetry, that broken symmetry can persist up to some critical temperature. And that is precisely what we see. We see a phase transition in classical Monte Carlo. So here, for instance, the specific heat versus temperature, you see a peak, then the peak characterizes a phase transition. The susceptibility shows a peak. There's a Binder cumulant that shows that it's a continuous phase transition. So this phase transition is in the same universality class as a three-state Potts model, which corresponds to Z3 symmetry. And the critical exponents are actually, the ones in the brackets are what is known for the three-state Potts model. These are numerical results. So you see that the numerical critical exponents are very close to the three-state Potts model. So this indicates that there's the classical model, the Heisenberg model J1, J2, and the ferromagnetic J3 will give you a Z3 phase transition. So that's all I have. Thank you very much. Thank you very much.
So these three states that you talked about,
yes,
they're not exactly equivalent, right?
Right. So there is no symmetry that makes them equivalent. It's a right. So I think it's an accidental degeneracy. Maybe that's it's very different. So there is no symmetry or operation that takes me from here to there. They just turn out to have the same. Right. Yes. Yes. So to me, it appears like an accidental degeneracy. Perhaps if you calculate the next order correction to the free energy, it might well be different.
There's 2D, DMRG calculations for the J1, J2 model.
Yes.
And if I recall correctly, all the studies that nail to whatever phase transition is less than J2 over J1, less than 0.5, right?
Right, yes.
But it seems that from your conclusion, it's going the other direction. Come on.
Yes, it does. So the phase diagram we had from ED looks like this. So it's still possible that over there you have a disordered phase. That could be spin liquid or something else.
Ganesh, so one comment, again, coming back to Deeptiman's question and then another question. Yeah, I also don't understand why do you call it a Z3 broken symmetry? It sounds more like an order by disorder to me. And perhaps then the transition is only like some T tending to zero thing, like temperature.
Okay.
Why is there a thermal phase transition to a Z3?
So let me say this. So the free energy expression is really a low temperature expansion.
Yeah.
So at very low temperatures, this is the correct expression to use. And at this level, the three states have the same free energy due to some accident.
And due to this approximation.
Which approximation?
You're doing spin waves, right?
Yes. Yes, but that's, for classical spins, that's allowed. Right? There's nothing, that's not a unphysical approximation. So if you think of them as purely classical spins at very low temperatures, this is a legitimate expression.
Okay.
So at least at very low temperatures, you have 3 equivalent states, and there is a Z3, there's a Z3 symmetric breaking. And now when you heat it up, it persists up to some temperature. So that's the picture I have.
And the second question was, you showed this phase diagram, right? Where there were these 3 things, like 2 ordered states and this incommensurate thing, and they were meeting at this highly degenerate thing. What happens if you heat the thing up? Is there like a classical fan or something like that? I mean, yeah, here. So if you heat the system up, then at some finite temperature, even in the ordered thing, do you see the correlations of this degenerate?
Classical model.
Yeah.
I don't know. I'm not sure. Yes. So here there are only 4 possible states, and they're all long wavelength incommensurate states. So I've not looked at them simply because they're really long wavelength spirals. So any finite system calculation might not capture them very well.
Yeah, so I guess just going back to the Z3 thing. So I guess, I mean, it seems to me like you're saying something stronger than that it's an accidental degeneracy. You're saying that it's an emergent symmetry at the critical point, right? Because the exponents are the exponents of the Z3 pot spot.
Yes.
Right. I mean, is that something that maybe that's something that you can prove perturbatively? Like you could start with a Z3 model and add some small, like the perturbations that are consistent with the actual symmetries of your problem and see if they're irrelevant at the critical point. I mean, it's something that maybe you can actually demonstrate.
Something you could possibly try, yes.
More questions?
Sure. Regarding this quantum phase diagram that you had and this force sublattice Plaquette ansatz, so does that state break translation symmetry?
It does in terms of entanglement, but you couldn't calculate it from any local observables. So not this one.
Yeah, but then Plaquette, so these shaded plaquettes are different from these unshaded plaquettes?
Yes, they are unshaded, but any observable you calculate is not sensitive to that. So this is like right. So in that sense, we are breaking this translation symmetry by hand in the state at least.
Okay.
But
It's more like a crystal then.
right. It is a crystal. Yes.
Okay.
Can you explain how you write down the entropy just in the slides after the summary?
This expression.
Yes.
So we assume an ordered state. Here it's characterized by theta and phi. I fix 2 parameters. That gives me a spin configuration. Now I consider small fluctuations about that spin state. And you can do an equations of motion. You can find that the low energy excitations correspond to spin waves, the brisk modes. They have a well-defined frequency or energy. They have well-defined energy and well-defined momentum. Right? So now, suppose I'm at very low temperatures, you expect that the deviation from the ground state will be very small. Therefore, the amplitude of these states will be very small. So we are justified in doing a linearized approximation, getting the spin wave energies to linear order. So you assume that the deviations are very small and you calculate the energies in response. And now you do a path integral of these spin wave modes, and so then you calculate the partition function, assuming that you have these different modes. Each of them has a well-defined energy, so it's e to the power minus beta e. That's the probability of one mode being occupied. Then you calculate the partition function, you get the free energy. I can show it to you on a piece of paper.